Hi, welcome to the problem set session for Lecture 7. This is the first one on probability and goes over some basics of probabilities. We're going to do a bunch of assorted probability problems. Okay. So the first bunch of problems all relate to this setup. Probability of some event A equals 0.3. Probability of some event B equals 0.2. And probability of some event C equals 0.4. Recall that these things mean there's like a 40% chance of C's happening. Okay. So first question. Let's start by assuming that A, B, C, and some D are mutually exclusive and collectively exhaustive events. Recall that mutually exclusive means they can't both happen at the same time, and collectively exhaustive means that the chance that any one of those happens, at least one happens, is 1. So they take up the entire sample space. What then is D? Well, we know the joint probability of all four happening, of one of the four happening, is 1, because they're collectively exhaustive. And because they're mutually exclusive, they can't both happen at the same time. So since only one can happen at the same time, the probability that D happens is 1 minus the probability that the other ones happen, right? Because D happens when the other ones don't happen because they're mutually exclusive. The chance that the other ones don't happen is 1 minus the chance they do happen. So you go through and do this whole thing, and you end up with D is 0.1. So that's probability D happens, assuming that A, B, C, and D are mutually exclusive and collectively exhaustive, right? And all this is saying is that the probability that D happens is 1 minus the probability D does not happen. And so we can write this like this. Not D. Well, what's not D? Well, these are mutually exclusive, so they can't all happen at the same. So no two can happen at the same time. So not D means either A happened, or B happened, or C happened, but not any combination of the two. So that's why not D is the same as probability of A plus probability of B plus probability of C in the case that they're mutually exclusive events. That's the first one. Second one, assume again A, B, C, and D are mutually exclusive and collectively exhaustive events. In that case, what's the probability of A or B? Well, the probability of A or B, if they're mutually exclusive, is just the chance that either A happens or B happens. Since they can't both happen at the same time, you can just add those two probabilities, and this is the probability that A happens plus the probability that B happens, which equals 0.5. This is only because they're mutually exclusive. This would not work otherwise, and we'll see examples of how it works later. What about if it's probably that A and B happen, again assuming they're mutually exclusive and collectively exhaustive? Well, if things are mutually exclusive, they can't both happen at the same time, so the chance that A and B happens is actually 0. So they can't both happen at the same time. Okay, number 4 we look at. If B and C are independent, so now forget about mutually exclusive and exhaustive, collective exhaustive, that's not true anymore. Now we're going to assume that B and C are independent events. What's the probability of B and C, assuming they're independent events? Well, for any two independent events, you can just multiply the probabilities together. So it's the probability of B times the probability of C. So that's going to equal 0.08. Okay. Fifth one. Finally, find the probability of E, some new event E, if the probability of A union E, so it's A or E, equals 0.5, and A and E are independent. Well, this is the trickiest one, so let's figure out how to do this. Now, in general, we can write this. The probability of some event X and some union some event Y, so this is A or Y, is equal to the sum of the probabilities, right, minus the double counting you do when you do that, right, minus the intersection of X and Y. The reason we didn't include this last term in the earlier examples in 1, 2, and 3 was because we had mutually exclusive events, so the chance they happen together, the chance there's an intersection, is 0. So the intersection of X and Y is 0. So we get rid of those things, but here we have to include that because these are not exclusive events. They're dependent, but not exclusive. Now, when two events are independent, we already said that the probability of their intersection is the probability of x times the probability of y. So we can go through and do this out, and we get the probability of x plus the probability of y minus the probability of x times the probability of y in general. So over here, what we get is that the probability, in our case, of A union E equals the probability of A plus the probability of E minus the probability of A times the probability of E. Now we want to rearrange this to get us the probability of E. That's the thing of interest here. We know this, we know this, we know these two, so we can move things. Well, we don't know this, but not this one. So we want to get these two together on the same side. We can do a little algebra and rearrange it and end up with probability of E is going to equal the probability of A union E minus the probability of A divided by 1 minus the probability of A after some algebra. Here that means 0.5 minus 0.3 divided by 1 minus 0.3 equals 2/7. So in this case, the probability of E can be computed, and it's 2/7. Okay. So this gives you a sense of how to use these ideas of intersection and union, of ands and ors, to compute probabilities, along with understanding mutually exclusive, independent, and collectively exhaustive. Okay. So that's that example. Okay. Now I want to do some sort of more basic calculations to figure out some more some probabilities. Oftentimes in probabilities, you have to use factorials. Factorial looks like that, so 7 exclamation point. That's 7 times 6 times 5 times 4 times 3 times 2 times 1 in general. 0 factorial is defined as 1. We don't do negatives here. So we can compute some stuff. What's 7 factorial over 8 factorial? Well, it's 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Note that this cancels with that, leaving 1/8. So there's an example of that, and there are more examples in the problem sets. This notation means 6 choose 4. It's the number of ways to choose 4 items out of 6 when you don't care about the order those 4 items are in. That's defined as 6 factorial over 4 factorial 2 factorial, because in general, n choose k is defined as n factorial over n minus k factorial and times k factorial. So this thing is going to be 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1 times 2 times 1. We cancel out this with that, leaving 30 over 2, so it equals 15. What about permutations? So what if we had the number of ways to choose 4 things out of 6 things when you care about the order that the 4 things are in? That's a permutation, and that's equal n factorial over n minus k factorial. You don't have a k factorial on the bottom. The reason is there are k factorial ways of arranging k objects. So if you don't care about the order, you divide through by that k factorial. If you do care about the order, you leave in the k factorial. So there goes that one. So now we're just getting rid of the k. So now it's the same as before. So now we have 6 factorial over 2 factorial. So n minus k is 2. This is 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 1. These cancel. 6 times 5 is 30. 30 times 4 is 100. What am I doing here? Yeah, 30. 30 times 4 is 120. And 120 times 3 is 360. So there we go. Okay, that covers that. Okay. So let's do that. Okay, so now we'll move on to other examples. Oftentimes we use probabilities to figure out the ways that things could happen, usually because those things are part of some larger problem. So here's a more concrete problem. A committee contains 8 legislators. So you have 8 total legislators. There are 3 men and 5 women in this legislature. Now you want to figure out ways to get a delegation of 2 people. So first, how many ways can you get a delegation of 2 people out of an 8-person committee? Well, that would be 8, choose 2. Since you don't care about the order here, that's equal to 8 factorial over 2 factorial, 6 factorial. Now, I hope you've now seen that 8 factorial is equal to 8 times 7 times 6 factorial. So that's divided by 2 factorial, 6 factorial. Those 6 factorials cancel, leaving us with 56 over 2, or 28. So 28 total ways to choose 2 possible legislators out of an 8-person committee if you don't care about the order or the makeup of the committees. What if you do care? What if you want an equal number of men and women? That means you want 1 woman and 1 man in your committee. So you're choosing 1 woman out of 5 possible women and 1 man out of 3 possible men. These are independent events, so we're going to multiply the chance that each one happens together. The chance that the number of ways you can choose we're going to multiply the number of ways you can do it together. The number of ways you can choose 1 woman out of 5 is 5 choose 1. The number of ways you can choose 1 man out of 3 is 3 choose 1. 5 choose 1 is just 5 factorial over 1 factorial 4 factorial. That's just 5. And the same thing over here. That's just 3, so this is going to be 15. Now, finally, last one, what if you want only women chosen? So again, you have 2 independent events. You want to choose 2 women from 5 and 0 men from 3. You get 5 factorial over 2 factorial 3 factorial times 3 factorial over 0 factorial 3 factorial. Remember, 0 factorial is 1. So this thing is just 1. This thing equals 5 times 4 times 3 times 2 times 1 divided by 2 times 1 times 3 times 2 times 1. These cancel. You get 20 over 2, or 10. So 10 ways of choosing a committee of 2 that only contains women. Okay, so that's that. So those are the sort of more concrete examples. I want to do one more example, which relates to Bayes' rule. Now here I want to go, for the example we have in the book again, but I want to add a little bit to the discussion that the worked example has in the book. So here we're going to do what's known as the Monty Hall problem. The Monty Hall problem is like this. You have 3 doors. Door number 1, that's the worst door ever. Door number 2, and door number 3. Behind 2 of these doors are goats. Why goats? I don't know, but they're goats. The third is a new car. I'm assuming you want cars more than goats. You want to find the car. You get to choose 1 door. To assume without loss of generality, you choose door 1. All the same doors, so it is without loss of generality to choose 1. Now, Monty Hall comes over and opens one of doors 2 or 3, revealing a goat. He always chooses a door that reveals a goat. And he asks you if you'd like to stick with the door you have or switch to the other door he did not open. You get whatever door you choose, either the one you have already or the door you switch to. And the question always in this problem is, should you switch doors, and why? The answer is, and if you want to pause and think about it for a while, pause the video. I'm not going to stop. The answer is yes, you should switch. Right? And the key is that Monty Hall's opening the door provides information, because he never opens the door with the car behind it. He basically tells you where the car cannot be. So just think about this. At first, you have a 1/3 chance of the car being behind any of the doors. You choose one of the doors, so you have a 1/3 chance of that one being right. That means there's a 2/3 chance that the car is somewhere in the other 2 doors. Now, if Monty Hall provided no information, you wouldn't bother switching because there's a 1/3 chance of each of the doors. So you're equally likely to have any of the doors work. But Monty Hall removes the chance that it could be behind one of the 2 doors because he opens it and there's a goat, meaning that the 2/3 chance that the car is somewhere in this region is now collapsed into a single door. Say Monty Hall opens door number 2. That means door number 3 has a 2/3 chance now of actually of having the car behind it. Right. So again, just to clarify, there's always a 2/3 chance that the car was in door 2 or door 3. Monty's opening the door number 2 does not change that at all. There's still a 2/3 chance that's behind door number 2 or door number 3. It is now you know it's behind door number 3 because Monty Hall opened door number 2. Since 2/3 is a better chance of getting a car than 1/3, you should switch. So this much is in the work part of the problem. I want to add a little bit of math here to show you how this works in practice and how you can get this out of Bayes' rule in practice. Okay. So let's look at the math. Assume again you pick door number 1 first, and Monty Hall opens door number 2. Okay, what you want is the probability that the car is in 3, given that Monty opened 2. Right, that's the situation you have here. Having opened 1 already, forget about 1 for now. You want to know the probability the car is in 3, given that Monty Hall opened door number 2. We can use Bayes' rule, which tells you that that's equal to the probability that Monty Hall opened 2, given car in 3, times the probability of the car in 3, divided by, now here's the tricky part, divided by the probability of opened 2, given that the car in 3, times the probability car in 3. I should have left much more room here. I'll make that shorter now. Probability of opening 2, O2, condition the car is in 1, times probability car 1, plus probability of opening 2, condition given car in 2, times probability of car in 2. So, why? Because the bottom has to be here, the probability of opening 2. The probability of opening 2 can be broken up into 3 disjoint events. The probability of 2 given that the car is in 3. The probability of 2, that's this first term. The probability of 2 given that the car is in 1, second term. And the probability of 2 given the car is in 2. That's the third term. But now we can fill this stuff out. The probability of opening 2 given the car is in 3 is just 1, right? If the car is in 3, Monty Hall is completely, and given you chose 1 already, Monty Hall will in fact open 2 every time. So this is 1. The prior probability of the car in 3, in fact all prior probabilities, is just 1/3. So we keep that. So all these are 1/3. They in fact all cancel out. So this is 1, 2. What's the probability of opening 2 given the car is in 1? Well, again, it's 1. If you chose 1, and Monty Hall had to choose between 2 and 3, I'm sorry, I shouldn't say it. Back up. The probability of opening 2 given the car is in 1 is a half. Right. Given the car is in 1, and given you chose 1, Monty can open either one of 2 or 3 with equal likelihood, because there's no information given away about the car. Oh, sorry, there's no, he can't reveal the car because the car is not in 2 or 3, so it's equally likely he opens 2 or 3. So this thing over here is a half. The chance of opening 2 given that the car is in 1 is a half, because he might open 2 or he might open 3 with equal likelihood. What about the probability that he opens 2 given the car is in 2? Well, that's 0. He never opens the door the car is behind. Therefore, this is 0. So, and I don't know what the C is, I apologize for, but you can go through and multiply it all out, and you get 1 times a third on top, divided by 1 times a third on bottom. So he always opens door number 2 when the car is behind 3, and you picked 1, plus 1/2 times a third. If the car is behind 1, which you chose, you can open either 2 or 3 with equal likelihood, so that's 1/2, plus 0 times a third. He never opens a door with the car behind it, so if the car is behind 2, he would never open door 2. So the 1/3s all cancel. We get 1/3 or 2/3. So this gets you what we discussed, what we got by reasoning through the problem. The probability of the car being in door 3, behind door number 3, given that you open door number 2, is 2/3. And Bayes' rule, in fact, gives us exactly what we got by thinking through it and just illustrating again that Bayes' rule is the go-to rule for incorporating new information in an optimal fashion. That ends this. The next couple of lectures we're going to discuss some questions about distributions. Thank you very much.